In Unit 5, Notes Part 7, we will be covering the families of the periodic table. The alkali metals are in group 1. These metals are shiny, have a low density, and are silvery white, and they are good conductors. Alkali metals are softer than most other metals, and they can be cut with a knife. They are also extremely reactive, and must be stored in an inert liquid such as mineral oil, and under an inert gas such as argon. Since alkali metals are so reactive, they are not found in nature and are isolated from other compounds. They have one valence electron and form positive 1 ions. The cesium clock is the most accurate type of clock yet developed. This device makes use of transitions between the spin states of the cesium nucleus and produces a frequency which is so regular that it has been adopted for establishing time. Cesium is one of the alkali metals towards the bottom of the group. In group 2, we have the alkaline earth metals. Alkaline earth metals are similar to the alkali metals in group 1, but they are definitely not as soft. They are shiny, they have a low density and they're silvery white, and they are good conductors. They are not quite as reactive as the alkali metals, and they do not react violently with water. They have 2 valence electrons and they form +2 ions. The emerald shown on the bottom left is a variety of beryl, a mineral that contains beryllium. Beryllium only occurs naturally in a combination with other elements in minerals. The transition metals are in groups 3 through 12, and they make up the D block on the periodic table. Transition metals are hard, they have high densities, melting points, and boiling points. They form compounds which are often paramagnetic, and they form colored ions and compounds. If you were to examine their electron configuration, they all have electrons within d orbitals. They are stable, but they tend to be able to form multiple oxidation states or charges. So for example, copper could form a +1 or a +2 charge. In the bottom left-hand corner, you can see some of the colored compounds that can form when a transition metal is bonded to an anion. The boron family is in group 13. This group contains the semimetal or metalloid boron, along with the metals aluminum, gallium, indium, and thallium. While the melting point of boron is high, the metals in this group have very low melting points. Gallium melts at 30 degrees Celsius, which means it would melt in your hand. These elements have 3 valence electrons and tend to form either +3 or +1 charges. If you've ever seen the disappearing spoon trick, this is done with a gallium spoon, which melts when it is submerged within warm water. The carbon family is group 14. This family shows the greatest variety of properties. There is a nonmetal at the top, carbon, metalloids in the middle, silicon and germanium, and metals at the bottom, tin and lead. Elements in this family have 4 valence electrons, and the most common oxidation number is a +4. While diamonds and graphite both consist of pure carbon, the difference in their structure results in very different substances. We know that diamonds are amongst the hardest substances known to man, whereas coal would be significantly less hard. The nitrogen family is group 15. There are nonmetals at the top, nitrogen and phosphorus, metalloids in the middle, arsenic and antimony, and a metal at the bottom, bismuth. Elements in this family have 5 valence electrons, and the most common oxidation number is -3. But they could also potentially form a +3 or a +5 in certain situations. Liquid nitrogen has a boiling point of -126 degrees Celsius. It is used as a coolant for computers, in medicine to remove unwanted skin, warts, and precancerous cells, and in cryogenics, where scientists study the effect of very cold temperatures on materials. For our first checkpoint question, we are looking at elements in the nitrogen family, which could potentially form a -3, a +3, or a +5. And we're trying to explain why each of these could potentially occur using electron configurations. Let's start off with the electron configuration of nitrogen. Nitrogen would have a configuration of 1s2, 2s2, 2p3. We know that nitrogen would like to be similar to a noble gas, so it's going to form charges that would make it more stable on its way to doing that. A -3 charge makes the most amount of sense, because if I were to gain 3 electrons, this p orbital would fill and it would become a 2p6, making it similar to its nearest noble gas, which would be neon. If it were to form a +3 charge, it would eliminate this 2p orbital. And while it wouldn't quite be a noble gas, it would still have a full stable subshell of 2s, since the 2s would be completely filled. Now, if it were to form a +5 charge, then the second energy level would be removed completely, and it would be similar to a different noble gas, which would be helium, since there would only be 2 remaining electrons. So that is the way that each of these 3 charges could potentially work for an element which is going to have 2 electrons in its highest s orbital and 3 electrons in its highest p orbital. The actual charges will depend on the amount of metallic or non-metallic character for each member of that family. Now for number 2, we are trying to figure out which of the following metals will be soft and extremely reactive. The most reactive elements are in group 1. They also happen to be extremely soft, so we are looking for a group 1 metal here. We do have group 2 alkaline earth metals, which are also somewhat reactive, but we wouldn't classify them as extremely reactive. So what we are looking for here is an alkali metal or a group 1 metal. Out of our possibilities here, that would be potassium. That is the only one of these 4 elements which would occur within group 1. The oxygen family, also known as the chalcogens, is in group 16. Most of this family, oxygen, sulfur, and selenium, consist of nonmetals. Oxygen is a colorless gas which supports combustion but doesn't burn, and is highly reactive. Sulfur is a yellow solid which smells like rotten eggs. Elements in this family have 6 valence electrons and tend to form a -2 charge in order to reach a noble gas configuration. Sulfur is unique in its ability to form a wide range of allotropes, which are different forms in which an element can exist. Graphite and diamonds are also examples of allotropes when we were talking about carbon earlier. So here we can see many different variations in which sulfur, pure sulfur, could form. The halogen family is in group 17. Elements in this family are highly reactive, somewhat similarly to the alkali metals in group 1, and they can be harmful or lethal in sufficient quantities. Fluorine is one of the most reactive elements, and it can even form compounds with some of the heavier noble gases which otherwise would not like to react. Elements in this family have 7 valence electrons and tend to form -1 charges in order to achieve a noble gas configuration. They are also diatomic elements, which means that they would occur in pairs in their elemental form. So for example, F2. Your thyroid gland absorbs nearly all of the iodine within your body. Because of this, radioactive iodine can be used to treat thyroid cancer. One of the main issues with many cancer treatments is that it could affect other parts of your body. So in this particular instance, if you use the radioactive iodine, most of it would go to the one particular place in which you are trying to treat, if you were talking about thyroid cancer. Our final family on the periodic table are known as the noble gases. Elements in this family are extremely stable due to having the maximum number of valence electrons their outer shell can hold, which is going to be 2 for helium and 8 for all of the other ones. They tend not to react, but larger gases like xenon can be forced to participate in some reactions when exposed to a small electronegative element such as fluorine. Noble gases also conduct electricity, fluoresce, are odorless and colorless, and are used in many conditions where a stable element is needed to maintain a safe and constant environment. We discussed argon use with the alkali metals earlier, so it can help to make sure that those elements do not react. While neon signs were popular for many years, LED lights are more cost efficient, safe, and require less maintenance. Once a staple of Times Square, they have mostly been replaced by large LED displays. For our next checkpoint slide, we're going to try to explain why each of these elements would have the oxidation states that are listed. Now, if we think about the Bohr model for calcium, calcium would have 2 valence electrons in its last shell, which means that it can either gain 6 electrons to completely fill in and become like a noble gas, or it can lose 2. It would rather lose 2 electrons. Chlorine, on the other hand, has 7 valence electrons, which means that it would prefer to gain 1 as opposed to losing 7, because that would be easier. Neon, of course, is a noble gas, so it does not want to form a charge at all. So it would prefer to have a charge of 0. So if I wanted to answer in general why each of these would have the oxidation states that are listed here, we could say that these oxidation states would allow the element to reach a noble gas configuration. And of course, our one element, which is already a noble gas, neon, would not need a charge because it's already achieved that configuration. So that concludes all of the notes for this unit. You want to make sure that you take advantage of all of the other resources that could be used to help prepare you for the next unit test. This includes all of the practice assignments on Kia. Remember that it is your responsibility that if you do poorly on any of the practice assignments, that you seek out help in order to improve. You should also make sure that you complete any of the labs that we have done within this unit. That includes the periodic trends graphing lab. You will definitely be asked questions about each of those trends and why they occur on the unit test. Finally, make sure that you take advantage of the YouTube channel. In addition to the notes videos, which can also be found there, you can find resources from each of the following content creators. For this unit, that includes Professor Dave Explains, Melissa Maribel, TED Ed, Crash Course, and Cod Academy.